Example 12, root locus analysis. So in this problem, we're just simply handed a transfer function, kgh, as provided here in the problem. So, and we can see very quickly that that this is actually the open loop transfer function that we normally would find. So rather than rewriting that, I'm just going to paste it into the next section. So we'll just go ahead and paste that here. And then the one thing that we can notice is that it's not in a very good form, and so we're going to have to rewrite that to be in a little bit better form because we want the s's to be alone. So there really is only one little problem, and that can be solved by pulling out a 0.2 from both parts of this term in parentheses. And so that gives us an s plus 5, and then we have 0.2k. The next step is to find the root locus gain, and in this case, it's right there, 0.2k. So we'll just write that in. And then we can move on to our next part of the problem. Now, this may be a little bit, you may be wondering, well, how can I really find the closed loop transfer function if I don't have the different terms shown in a block diagram? And so in order to do that, and you can see that back in the problems that we've done before, there really isn't a lot to do with that. And I'm just going to go ahead and, just like the last couple, I'm just going to go ahead and show you the closed loop transfer function. So you notice the similarities here. We've got this right here, the 0.2k times s plus 5. That's the numerator right here. That's the forward path of the system. And then the denominator is just this s times, I'm not going to be able to get it all, but the s times s plus 1 times s plus 2. And we can see that right here. So we've got the kgh in terms of the entire numerator and part of the denominator. And then you can see that we are adding the forward path to these other two terms. And that you'll see that over and over in the problems that we've done up to example 12. So if we just take what we have here and do the multiplication of the s times s plus 1 times s plus 2 plus the 0.2k times s plus 5, we get this new, so you notice the forward path remains the same, and then the denominator is a third order system, third order transfer function, or third order polynomial, s cubed plus 3s squared plus 2 plus 0.2k, those are just, k is just going to be a number, times s, and then finally with a k. So then we'll go ahead and we'll determine our poles and zeros from this. Remember, you can find the poles and zeros from this transfer function, but remember, we're going to let k vary so that they change over the range of k. So this polynomial is going to take on different poles or different roots based on what k is, both here in the 2 plus 0.2k as well as the just plus k here at the end. So when we find the poles and zeros, we're really finding the initial poles and zeros when k is equal to 0. That's capital K is equal to 0. So So the poles and zeros are just found from the open loop transfer function. So we can just put 0, -1, and -2. And then for the zeros, the 0 in the numerator is just -5. So then we can, when we go to find the branches, we know there's 3 poles, so there's going to be 3 branches. Okay, and then our next step, of course, is to determine where the poles and zeros are. So I'm gonna move this up a little bit to give me some space, and we'll draw the pole zero map. And let's see. I'll use blue for the imaginary real axis. And I've got poles at 0, -1, and 2, and a 0 at -5. So we'll go 1, 2, 3, 4, and 5. And then we'll go ahead and we'll draw in the poles and zeros in red. So we have a pole at 0, we got a pole at -1, and we've got a pole at -2, and then we've got a 0, 3, 4, 5, so -5 right there. And then we can determine where the branches would be located, and we'll use purple here for Easter. So let's see. In this region right here, are there poles and zeros that are, when added together, are an odd number? Yes. We've got 1 pole to the right of that. So there is a pole, or there is a branch, possibly 2 branches between these 2 poles. What about here? Is there a branch there? And the answer is no, because we've got 1, 2 poles to the right of it. That's an even number, so there can't be a branch there. What about a branch here? And that one, yes, because there's 1, 2, 3 poles to the right of that branch, making that an odd number, and so the branch exists. Now, there's 3 branches, so just from doing a few problems before, we know that probably this pole is gonna this pole is gonna move to the left towards this 0. I'm talking about these 2, and then these 2, those 2 are going to go towards each other, and then they're going to break away. So we can see that this one right here, that's going to be 2 branches, not just 1. Okay, so that tells us a little bit about where those poles are located. And then I'm going to go ahead and just add to this right here some information so that you can see the thinking between, which is what I did for the branches. Okay. All right. Now let's go to the asymptotes. And for the asymptotes, we can see that for the location of the asymptote, we use the expression for sigma sub a. That's the location where the asymptote crosses the real axis. So we've got it doesn't like that I'm on the equation when I do that, but here we go. So we've got the 3 zeros, or the 3 poles. There's -0, -1, -2, minus the 0 at -5, and there's 3 poles minus 1 0, which is 2. So it's going to be negative 3 plus 5 over 2. That's 2 over 2. So the asymptote's going to be right here. Right on that pole that's also at, excuse me, that is not correct. So you get to have on video my mistake here. That's plus 1. So that's going to actually be located right here. And there's no problem with the asymptote being on the left side, the right side of the imaginary axis, because that's the asymptote. That's not necessarily the location of the poles. So the next thing we do is find the angle of the asymptote with gamma. So we're using this formula here, this 2n plus 1 times 180 over the number of poles minus the number of zeros. So plus or minus 2n plus 1 times 180 over 3 minus 2. That's going to, this is going to be equal to 2. That's going to divide 180 degrees by 2 to make it 90. So this is our final expression. And so for gamma, for n equals 0, gamma is going to be equal to 0 plus 1 times 90, so plus or minus 90. For n equal 1, that's going to be 2 times 1 plus 1, that's 3. So that's going to be plus or minus 270. And plus or minus 270 and plus or minus 90 are the same angle. So it's repeating, so we can just, forget it and move on. So basically this asymptote is going to be straight up and down. So the next thing we can do is, we could actually draw a rough root locus right now. I don't want to make you feel like we really need to go and find the breakaway points. I'm going to do it because I want you to see the breakaway points, how we do that. But there's really not much to this part of the problem, because the breakaway point is going to be somewhere between the 0 pole and the -1 pole. And I mean, for one, for any amount of accuracy, we'd have to make this a lot wider between 0, -1, -2, and so on to really see any difference. But most likely, it's going to be close to the center. And we're going to find out the exact value, and you'll see what I mean. But we can actually write this now. And so I'm just going to do something here real quick. I'm going to go ahead and draw in the root locus right now before I go any further. And that way you can, the finding of the breakaway points is just a kind of an added bonus. So first off, there's a branch here between -2 and -5, and that's just going to be like that. Okay, so that's one of the branches. So as k gets bigger, this pole right here is going to move to the left toward that 0. Okay, now these two, the -1 and the 0, they're going to come to the middle. And then they're both going to break away. One's going to go up and one's going to go down. And what they're going to do is they're going to, as the poles change, they're going to go towards being tangential to the asymptote. So it's going to do something like this. And I don't know why that just turned black, but it did. and that one turned red. But this is really bad. I'm going to show you a better one in a little few minutes. But that's really what that one does. So you can see that as K gets bigger, the poles are going to eventually go to, to the either the unstable side of the imaginary axis, unstable. So we've got to make sure that we pick a value of K that's like, kind of in this region right here, and I'll erase that in a second. But in that region there, because the poles are imaginary, they're not real. They've got an imaginary part if they're up above the real axis and below the real axis, but they're and that will make the system have oscillation, but they are on the left side of the imaginary axis, making the system stable. So really bad drawing, but once we've done this, once we realize what we've got, we can actually, and we note that these are this is a pretty simple problem with these two poles close together. The breakaway point's going to be in between them. So we can draw that. And again, the sketch is really bad, but hopefully you get the idea that we can draw that root locus without really knowing the location of the breakaway points. Now that we've done that, though, let's go ahead and find the breakaway points. So I've got a couple of methods to do that. Method one is the one that we've been using for a while. You can see we've taken the general expression here and we've put in our pole side and our zero side. And so we've got an expression. We've got to solve for sigma b. So we've got to do a lot of algebra to get there. And you can see we do that by multiplying each term by these terms so that the denominators canceled out. Once we do that, then we have a bigger expression, but we don't have any denominators. I'm going to replace sigma b with x just to make the expression easy to read. And then once I have that, I can use Wolfram Alpha or MATLAB, and you can see I've got 3 values. I've already highlighted the right one, but let's look at each one to determine why it can't be this one or this one. So the location of negative 6.94, that is actually, and I'm just going to scroll up again here, that's going to be located out here. So there's no branch out there, so that can't be a breakaway point. And this right here doesn't have a breakaway. It never breaks away. So the breakaway location has to be between 0 and -1. So that helps us to choose the correct value here. And you can see this one, this -1.61, that's in a region where there is no branch, so it can't be that one. Can't be that one. So it's got to be this, and that is almost right in the center between 0 and -1. So it makes a lot of sense, and that's a good way. A lot of work, that I've kind of skipped here. Didn't really show all my work because I've done it a couple times, and it's just algebra. Everybody in here ought to be able to, solve for sigma sub b and use Wolfram Alpha or MATLAB to calculate those things. So, so that's method one. So let's look at method two. So this is the one, method two uses the derivative. Probably should have written that there. It's a min-max problem, really. So first of all, we take our open loop transfer function, and I'm not very specific here, but you can see KGH. If I bring GH over here, I've got an expression for the open loop transfer function. Once I get K by itself, then I've got, here's my open loop transfer function. Notice that the little K has been moved out of there because it's over on the other side. But once I get my expression for K all figured out, not 1 over K, but K by itself, then I can take the derivative with respect to S, set it equal to 0, which is part and parcel of a min-max problem, go through the derivative part, and then I'm going to get a polynomial. I'll take the polynomial and I'll combine terms, and then I'll use Wolfram alpha or another tool. And again, I find 3 roots to that, and there's our negative 0.45. So that's another method. Let's see here. On this page, I just am going to show you the final solution. It's not awesome, but it is a little bit better than the last one. So you can see I've got the location of the asymptote. I've got the pole at 0, the pole at -1, the pole at -2, the 0 at -5. I've shown the branch between -2 and -5, and then I've shown the poles from 0 and -1 coming together, breaking away at this point, which is about halfway in between them, -0.45. And then I make a nice curve that goes tangential to the asymptote as the curve goes to infinity. So this is heading to infinity. I should say negative infinity, and this is infinity. So now what is this? This is our 50-degree line. Those dashes, and that's showing you that we don't really want to be anywhere here. We don't want our poles to be in these locations because these are going to provide more instability for sure if we're on the right side. But even this area right here, it's not unstable, but there's a lot more oscillation. Overshoot's going to be higher, and so we want to get in between the 50-degree lines. So our value of K needs to be less than whatever it needs to be below, these 2 points. So, and we'll get more into that over time. But that concludes example 12, and there will be some other examples for you to follow in the class as well. So that is all.